What happened? Oh, I'm going to my dad's, what's it called?
Yeah, I just.
Right appreciation.
Yeah, a lot of people did. I got a lot of bar graphs for box plots.
Yeah, what's a box plot?
It's the one that does the core power.
It's got the 5-number summary. It's like the box and whisker. So you draw a rectangle from Q1 to Q3 with Q2 in the middle, and then Q1 and Q4 are the whisker.
Not even a sad face.
Yeah, there were a lot of sad faces for the box plot.
You should have all given us at least.
If you gave me
Must have really done
Did it wrong.
No? I don't know.
So a couple of observations from your tests. So SOCS stands for shape, outliers, center, spread. When we say shape, there's 3 answers you can give. Symmetric, skew left, or skew right. When we talk about skew left or right, the left or right is the direction of the tail for your skew. So like, if your distribution looks like that, the tail is over here, so we say it's skew. Tail's over here. Let me do it this way.
Where's the
right.
Skew right.
oh.
The tail is over here, right?
Question, what's 0 out of C?
Huh?
It looks like it says 0 out of C. Maybe I'm crazy.
That's okay.
Oh! Yay! I got something.
Okay. I think you had a number wrong somewhere else, but your graph is reflective of your numbers that you recorded. So I said it was okay, even though the graph is technically wrong.
Thank you.
But like, you counted something wrong earlier.
Oh, yeah.
I think in your frequency table. So like, your graph was wrong, but like, the only reason it's wrong is because you did something wrong before.
I got it.
So I didn't want to like double count
I appreciate it.
wrongs.
Really appreciate that.
At least if there's evidence of like how you got it, the reason you got it wrong was for something silly.
Yeah. That makes sense.
When we say outliers, we know what outliers mean, right? Center. What kind of answer should you give for center? Should you give a mean or a median? That's all you need to write down. Like the mean is about this or the median is about that, right? Or if you calculate it exactly, great. The spread, what do you write down for spread? Standard deviation, range, or IQR. Any of those would be appropriate, but you need a number there. Okay, SOCS, I don't know that anybody did that entirely correct in here. So just shape, outliers, center, spread. Shape is symmetric, skew left, skew right. Outliers we've talked about, I think we're okay there. Center is mean or median. Spread is range, IQR, standard deviation, something like that. Okie doke. All right. Today we're going to start chapter 13. We'll do, say, about an hour of chapter 13, and then if you haven't submitted a proposal for your IA yet, I need you to seriously get on that. If you've been going back and forth with me about something and we need to have a discussion, there'll be time to do that. So there's a couple of people that I've have sent stuff and I've rejected for reasons or that are kind of still kind of nailing down their design for their data collection that we're still kind of going back and forth with. If any of those people need to have a conversation about what's going on, we can do that then also. We won't finish this section 13.1 because it's a pretty big beefy boy here. But that's what the plan for today is. Sound good? All right. This topic that we're going to be doing in chapter 13 is, I think, technically the most difficult thing that we do in first semester. So while the actual bones of what you're going to be doing, the calculator is going to handle, but understanding what the calculator is doing and what things mean can be a little bit tricky. So really kind of like you to pick your heads up and put away your shopping tabs and power down your earbuds and kind of really dial in here for an hour for me. Is everybody okay? All right. So what we're going to be talking about in chapter 13 is hypothesis testing. But really what we're talking about is how do you know that something is different? Mathematically, right? You do, you do an experiment, right? Where you changed one thing. How do you know that the results you got are actually different and not just you got a weird sample, right? So statistically, we can give support for or against something happened here. Everybody okay with that idea? You guys in psych, anybody taking psych or took psych? You guys talked about hypothesis testing and when you did statistics. So you have a little bit of a leg up on the competition, which is cool. All right, so let's start. We're going to just kind of dive in with an example. So suppose that you're trying to figure out how long on average it takes to install a new graphics card system, or a new graphics card in a system, like in a computer. The old card installation took, on average, 2 minutes. So X bar or mu, we can use interchangeably as our symbol for a mean. And we had a standard deviation of 0.2 minutes. So again, that sigma is our standard deviation symbol. And now we got these new graphic cards, and we believe the mean time for those is 2.2 minutes to install. What we want to do is decide, are they really taking longer or not? Is that really a difference, or is it just because our sample of new cards is small, or something weird happened, or you got a defective one that took longer than usual, or something happened, right? So when testing these new installation times, we want to know if there's a reasonable chance of getting a sample whose average is 2.2. So could I have gotten the same 2.2 average from the old cards if I did a sample? Is that something that was likely to happen or unlikely to happen? If it's pretty likely that I could have also gotten a 2.2 mean from the old card installation, then is the new card installation probably really any slower? Probably not, right? If it's really rare that I could pick a sample of old card installations and get that mean, then there's good evidence that this new card installation is meaningfully slower. Everybody's okay with that idea? Now, we haven't talked it out about how we're going to do this yet. Talking about calculating these probabilities, and we'll get to that eventually, but just this is kind of giving the motivation for what we're trying to do here. And that's what I just said. Okay. So, again, we're talking about this graphics card installation system. So let's say that this is my distribution for the old card installation. So this is my mean at 2, right here in the center. How do I know the mean is going to be directly in the center of this distribution? Because the shape is symmetric, right? In general, this type of distribution is called a normal distribution. We'll talk more about those later. But if this is 2.2, this little area underneath my distribution will represent the probability that I get a sample whose mean is 2.2 or less. I calculated that area to be 7.6 times 10 to the negative 24. Is that a big number or small number? Really small, right? Very close to zero. So is it likely or unlikely that I would have gotten a sample from my old cards that would have a mean of 2.2? Really unlikely, right? What would that tell me about these new cards? It is actually taking longer to install them on average than the old card, right? The installation process is going to be longer. Okay? Or at least we have strong evidence to support that claim. We haven't proven anything, because you can't really prove something like that, but we can provide statistical evidence. Does that feel okay? So it's basically impossible that I would have gotten a sample of the old video cards and gotten that kind of a mean out of there. Almost zero. Like struck by lightning, winning the Powerball kind of odds. Yep. Okay. So we just said all those things. All right. So let's talk about actually doing the statistical test now to get these probabilities and discussing like how to do that. So we're going to start with two hypotheses. So the first is the null hypothesis. We abbreviate that with the symbol H0. So this is what we're trying to prove. So we start by assuming that that hypothesis is true, and then our statistical test can either support or reject that hypothesis. So in that last example, our null hypothesis would be that the new installation time is the same as the old installation time, in that the two video card installations are really the same, that the mean would be 2. Everybody's okay with that? Then we write an alternative hypothesis. We abbreviate alternative hypothesis either H1 or HA. They can be used interchangeably. This is the opposite of what we're trying to prove in the null hypothesis. So we can't prove a negative, like prove to me that Bigfoot isn't real. There's no Bigfoot. What would you have to do to prove that? Like you'd have to check physically everywhere on the planet all at the same time, right? And that's not possible to do, right? You just can't prove a negative. So if our, so we don't have like, you never prove like the alternative hypothesis, but you find evidence in support, right? Does that make sense? Now, if you find that the null hypothesis is supported, then that instantly means that the alternative is rejected. Or if you find that the alternative is supported, that means the null is rejected. Does everybody feel okay there? That the two can't happen at the same time because they're opposites? So in our last example, our alternative would be that the mean time for the new graphic card installation has a mean that's greater than 2 minutes. Notice that that's not exactly the opposite of equals 2 minutes, right? So we'll look at what that means in a second, but depending on what you're trying to, like the data that you're given, you may not have not equal to, you might have greater than or less than as your alternative. Okay. So to do this kind of a statistical test, this is called a t-test. Psychology people, does that ring a bell? So very common in like medical testing or, like social sciences to like you do an experiment and you want to see if like, did something different happen here? This is often your go-to. So let's work through an example here together. So it says a factory produces light bulbs that are known to last for 8,000 hours on average. A new type of light bulb has been developed by engineers, and it's claimed to last more than 8,000 hours. But management is concerned that the cost of the process of producing the new type of light bulb, that's more expensive than the traditional method. And if it doesn't really last more than 8,000 hours, is it really worth it to us to change our process to make a better light bulb if it's more expensive to do so? And I'm not really convinced yet that light bulb will last longer than the one we're currently making. You see the conundrum? We need to figure out, like, is this actually a better light bulb before we go and make the change and cost a whole bunch of money? Like real business kind of decision, right? If you're an industrialist or something. Okay. So again, we can justify changing to the new process if we have evidence that the new light bulbs have a longer life than 8,000 hours. So we took a random sample of 25 of these new light bulbs that came off the assembly line, and we tested them. And we found that that sample had an average lifespan of 8,600 hours and a standard deviation of 1,000 hours. Okay? So can we use that evidence to either support that this new light bulb is actually lasts longer than the old one, or are they really the same? Is it still just like an 8,000 hour light bulb and we just got a weird sample? Everybody's okay? All right. Blah, blah, blah. So we'll start by kind of setting up our known data. So the mean for the original light bulbs, which I'll abbreviate mu0 with a subscript 0, that's like null, like it's the mean for the null, is 8,000. The mean for our sample, I'll represent as x bar, and that's 8,600. The standard deviation for our sample is 1,000. And now we're going to write our two hypotheses and show you how to do this t-test. Okay, so just written down what was given to us. So our null hypothesis is going to be that nothing happened, that the two light bulbs are really the same. So we'd say the mean is 8,000 hours. The alternative should be is the mean bigger or smaller than 8,000? Or just not equal to it all? Which one should I pick here? Bigger. Why? Because we're trying to show that the new light bulb lasts longer. That's exactly right. So it was basically told to us in the problem. So my alternative is that the mean is actually bigger than 8,000 hours, that this new light bulb is actually a better light bulb. So far, so good? Okay. So now let's go ahead and calculate this probability that I could have taken 25 of my old light bulbs and gotten a sample that has that mean and standard deviation from it. So to do this, we're going to use what's called a one-sample t-test. No one, either me or the IB, is going to ask you to ever do this by hand. We're always going to use the calculator to do this for us. We will be asked to be able to interpret the results of the t-test and explain what's going on or what things mean. Everybody's cool? I know that's hard. The explain part is sometimes tricky, right? All right, so if you have your graphing calculator with you, please take that out and follow along. If you'd like to follow along and you don't have a graphing calculator with you, I have 4 sitting here on my desk that you're welcome to borrow for a class period while you follow along with what we're doing. So, you should start by pressing the Stat button. Once your calculator is turned on, you'll press the Stat button. And then you'll move over to the Tests tab. And you will move down to the t-test, which is option number 2. So where it says mu naught, we'll have 8,000. Where it says x bar, we're going to type 8,600. Where it says SX, we're going to type 1,000. Where N is, we're going to type 25. Where did this 25 come from? If you
Mine says list and frequency.
for t-test?
Yeah.
Oh, it's because you're on data still, not on the stat tab. Just your up and down arrows.
So the right hand.
Also, man, that cool. That's cool.
Okay, so yes, Jack says that N was the sample size. Remember, we sampled 25 of the new light bulbs. So N is the sample size. And then here we have to write down our alternative hypothesis. So we said mu was greater than mu naught, right? So if you look down here, it says mu colon, and then we have 3 options. Either it's not equal to mu naught, less than mu naught, or greater than mu naught. So we're doing a greater than. So let's make sure that's highlighted. Everybody's okay? So if we go ahead and hit calculate, this spits out. If we had hit draw, this is the picture we would have gotten. The part that's shaded, it's drawing the shaded thing like we saw before, is this little, it's way over here where you can't really see it because it looks like it's right on the x-axis. So the 2 numbers that we have from our result that we need to interpret are the t and the p. So the t value is called a critical number. And basically it tells us how far away from the mean our distribution is from the original mean. So if the original was, mean was 8,000, basically it's saying this 8,600 is like 3 steps away. So like 1, 2, 3 steps away is where like the 8,600 is. Which is fine, but the number I really care about is the p. The p is the probability. Basically what this is saying is that's the probability of getting the same sample from the old light bulbs. That probability is pretty doggone low, right? What can we say about this then? So the new light bulbs really do last longer, right? That's what we're seeing, because the odds of getting this kind of a sample from the old light bulbs is pretty doggone rare, right? Like 3 in 1,000. Does that feel okay? Yes.
When I hit draw, like is there
What does the error say?
this is invalid.
It's because you have one of your plot 1, 2, or 3 turned on, and there's no data in your editor. So if you do the y equals up at the top, it says like plot 1, 2, or 3. One of those guys is highlighted. So if you turn that off and then do the draw, you should get it.
You're solving, does it matter whether you calculate the draw? Should we do it both?
I usually like to calculate because I get more decimals from my p, but it doesn't really matter. I mean, if we ask for 3 sig figs, that doesn't have 3 sig figs on it. You know, that's the risk you run. Because it's only going to give you like 4 decimal places or whatever here. Okay. So what does this mean? We just said there's almost, very rare chance that we could have gotten the same sample of old light bulbs. So it sure seems like these new light bulbs are better. They are lasting longer than the old ones. So we would say that we reject the null hypothesis that the 2 light bulbs are the same, and we accept the alternative that the new light bulb really is better, that it's lasting longer. Its average lifespan is longer than 8,000. Is everybody okay with that idea? So those 2 words, accept and reject, should be part of any answer, right? We accept, this hypothesis, and we reject this one, and then you say in words kind of what that means. Does that feel okay? All right. So what we've just done here is called an upper tail test, because if we go back and look at our graph, we're looking at the upper tail, like greater than. If we had done a less than, that's a lower tail. And if we're looking at not equal to, we'd be looking at either end. That's called a two-tail. So we're going to just kind of go through and do a little bit of example showing these different tail tests. So say we had that same scenario with the light bulbs, but this time our sample mean had 82 or 8,200 hour average. So that's our sample, that's our new light bulbs. So everything else stayed the same. We set it up, and I run and look at the probability here. Like 16%, right? Here you can see when you do the draw, you get can really see some area shaded. Again, this is still a upper tail. If I had done say a lower tail, what if the alternative is, what if these light bulbs actually worse, right? What's the probability that those would have turned out worse? There, the probability is real big, 83%. Whoa! So that's really saying that, what's that saying? That saying that they're really the same, right? It's very likely that I could have gotten a sample of old light bulbs that had that kind of a mean. And the last kind is a two-tail, where I assume that the means are just not equal, so it could be bigger or it could be smaller. So if I do the draw, I get something like this, and I get a 33% probability or so. Now, the question here that we should be asking ourselves is, okay, Mr. Kulik, when the probability is like almost zero, it's really clear that like something happened that I should be accepting the alternative. When the probability is really high, when it's really close to 1, that's pretty clear that nothing's happened. I should accept the null. But what about like some of these things that are kind of in between? Like how high does that probability have to be before I, like accept the null and reject the alternative, or vice versa? Like where's the cutoff line, right? That's the question to ask, because we're starting to see like, yeah, that probability might not be super obvious as to where that cutoff is. Everybody's okay? All right. So yes.
So if it's like closer to like 0, that means that it's like correct. But if it's like if the percentage is like super close.
So let's stay away from the phrase correct.
Yeah.
So if the probability is close to 0, that means that that the two things are different. That the alternative is what we're taking.
Okay.
If it's very close to 1, then it's clear that the two things aren't very different, and they're really accepting the null, that nothing is really happening. So again, we did 4 of these little t-tests here in an example. Now, pretty clear that the probability our null hypothesis is correct, is pretty dismal. Like it's pretty clear that something happened there, the light bulbs are different, that the alternative is correct. And here, the probability is very high, that's really close to 1. Pretty sure that in that case, the alternative is wrong and the null is correct. But what about these guys in the middle? They're like, well, I don't know, is that a big number or not a big number? It's pretty far from 0, but it's still a long ways from 1. So what we need some kind of standard as to say, okay, what kind of probability is like our cutoff here? So when we set a standard like that, it's called the level of significance. This would be something that would be given to you in your problem. So it's basically the cutoff line between how bad of a sample is bad enough, right? So typically your most common levels of significance would be like 1%, 5%, or 10%. But it could be anything. You could have a 7% level of significance if I wanted to make one. That's not very standard, but so that's basically saying your cutoff. Like once you're bigger than, if you're using a 1% level of significance, once that probability exceeds 1, we accept the null and reject the alternative. It's basically, there's your cutoff. That's how good we want this to be. Now, why do we have varying levels of significance? It's going to be, how sure do you need to be that these two things are different? What's an industry where you better be doggone sure that something is different before you put it to market? Medical stuff is like, you don't want this screwed up, right? If we say that this is actually medicine and it's going to help, we better be darn sure that like something's actually happening here, right? What's an example of an industry where like it might not matter that much? I think the light bulb example we just looked at is something where if the new light bulb really isn't that much better than the old light bulb, or isn't really different at all, like nobody's dying from this. Your company loses some money, which you don't want to have happen, but you probably don't need to do the level of testing at a 1% level of significance, right? If you have good, like if the engineers are like, yeah, this should work, this should be better, like we've designed something that's better, we're confident it's going to be better, like your numbers don't have to play out so stringently to be, like to a 1% chance that this was, like it'd be a little cheaper. And that's the catch here. To do a test at 1% level significance, tends to get more expensive, right? Because it's possible that the two things are pretty different. It just, like that's a pretty high bar to cross. Okay. So how do we use the level of significance with our p-value? So when p is small or less than your level of significance, we reject the null and accept the alternative. When p is bigger, we do the opposite. So again, here's the summary. And this is something that, like, again, you will have to do this on the test. This is one of those things that you have to have memorized. We're not going to have it on the equation sheet on how you know to accept or reject. Okay? Have to have it memorized. So if the p is greater than or equal to, note the or equal to, the level of significance, we accept the null and reject the alternative. And in the opposite case, if p is less than the alternative, we reject the null and accept the alternative. Got to have those two memorized. Okay? It's easy to screw up because it's just like, but we got to have it. I'm going to tell you that right now. Not a lot we memorize in this class, but that, whether we accept or reject, I will not tell you when you ask me on a quiz or a test. You have to have it memorized. Everybody's okay?
Wait, where's that written?
And the previous slide. Cool? All right. And here it is in summary. All in one slide. So here's a technicality here as far as when we write down our final answer on a test or quiz. Now reject is fine to say. Except what I would prefer is that instead of saying we reject the null and accept the alternative, I'd prefer if we said we reject the null and find evidence in support of the alternative. Because we don't know the alternative is correct. We can't prove a negative, right? What we've done is we found evidence in support. We think that it's right. And if you stack up enough evidence in support of it, we just generally accept these things to be true. This is how science works, right? We don't actually ever prove anything is correct. We just prove things are wrong, right? You can just reject hypotheses, but you never actually prove it correct. You just fail to show that it's wrong. We do this for a long time, right? And you guys in physics? For physics, we accepted the Newtonian model of gravity for a long time until the 20th century rolled around and some scientists like Einstein started to find experiments that showed that, well, actually it's not fully right. Because we've shown instances where now this doesn't describe what we're observing. So gravity turns out to be more complicated than Newton had thought. And we created a new model to describe gravity. But that's an example for 100 plus years. It's we got it, we solved it. And then we finally got enough technology to test some of these different scenarios. And it's ooh, not now, it doesn't work. So we need to go back and create a new model. And that's just in general how science works, right? Nothing is proven, even if we found 100 years of evidence in support. All it takes is one experiment that's oh, something's wrong. Okay. So again, if you can say evidence in support of, or you could say fail to reject, I guess is what I wrote here. Instead of accept, fail to reject, or evidence in support of. are also acceptable, but try to stay away from the term accept unless we're having like casual conversations here, right? If you're writing something down for a formal answer, let's try to speak precisely as a mathematician. Now, when we're just talking in class, we can be informal. It's okay. All right. So, since we're talking about a p-value, you're really never going to get a 0% p-value or 100% p-value. So there's always a chance that you thought two things were different and they really weren't, or you said two things were different and they're really the same, right? Can someone think of an instance in recent history where this came to like popular attention in the media? Think back like, 4 years or so ago. COVID. What did everybody have to do at one point during COVID? Well, what else would you probably have to have done? How did you know if you were sick? You took a COVID test. Were those things 100%? No. Sometimes it said you were sick and maybe you really weren't. You got a false positive. Or sometimes they said you weren't sick, but you really were, and you got a false negative, right? That's what we're talking about right now. So let's say that we have the situation where we have either the alternative or the null and the alternative. And let's say this side represents the truth and this side represents the result. So if we said that we do not reject the null, and the actual result was that the null was true, then no problem, right? That's a good test that we did. If we rejected the null and we said the alternative was true, that's a good result. That's exactly what was supposed to happen. But what happens if we didn't reject the null, but really the alternative was true? Or we did reject the null, but the null was actually the true one. So we had correct decisions here. When we say we reject the null, but it was actually true, that's a type 1 error. And if we do the opposite, if the null isn't true, but we accepted it, then we have a type 2 error. Let me just Google something really quick. Yeah. So the type 1 error is like the false positive, and the type 2 error is the false negative. In general, if you're doing something like a COVID testing, which one would you want to minimize? Which one is more dangerous? The false negative, telling somebody they're not really sick when they really are sick and they go and infect a bunch of people, right? If we have a false positive and somebody quarantines themselves unnecessarily, well, that's inconvenient for the individual, but it doesn't pose huge problems for the population at large. If you send a sick person back to work or school or whatever, and they get a whole bunch of people sick, that poses big problems for the population at large. So depending on the scenario, the person that's designing the tests is going to shoot to maximize or minimize either type 1 or type 2 error, depending on the circumstances. So you guys, the Olympics were this summer, right? As part of the Olympics, to make sure that there's no cheating going on, what happens? Drug testing, yeah. So one thing that you don't want to do in an Olympic for drug testing is to give out a false positive, right? Tell somebody they're cheating when they really weren't. Do you know what they do to help minimize that? Part of the test protocol? The multiple tests. They split the sample into 2 lots, an A sample and a B sample. And if the A sample comes back positive for drugs, they then run the B sample and make sure they also get a positive result there. While that doesn't eliminate the possibility of getting a false positive, those two probabilities work in like multiplicativity. So if you get two positives, the chances are fantastic that you really are positive, that the false positive is almost out the window. It's lightning strike territory. Okay. So we'll do this one last example, and then we'll take our break here, I think. That in a comparison of nicotine that could be inhaled from cigarettes of the same brand, we found that maybe that's different in different countries. There's some suspicion that the local cigarette companies are boosting their cigarettes' nicotine content in order to maintain or increase present addiction levels. So what we've done is we took 40 randomly chosen cigarettes and compared the nicotine content between 2 European cities. So let's say in country A, we found the average nicotine in those 40 cigarettes was 0.85 milligrams per cigarette with a standard deviation of 0.2. And in country B, we found the 1.3 milligrams per cigarette with a standard deviation of 0.18. And we want to test, is the nicotine content really different in these two countries? Or do we get a weird sample? And we're going to test at a 5% level of significance. So we want to know, like, okay, we didn't test all the cigarettes, we just tested a couple of them. Is it possible that I got, like, 2 weird samples that look different, like one has low on nicotine, one has high on nicotine, but they're really kind of still the same sample? So again, we have 2 different testing lots that we have, right? 2 different samples we've taken. So the type of t-test we're going to do here is called a 2-sample t-test. So pull out your calculators. We'll run through how to do this on your calculator. Blah, 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 blah. So we start by writing our 2 hypotheses. Hypothesis 1, the null is that the nicotine's the same in both countries. So we can say that the 2 means are the same, or that their difference is 0. These are both equivalent ways to say the same thing for a null hypothesis. Or the alternative is that the nicotine content is different. So we can say that they're not equal, or that their difference is not 0. Either of these approaches are fine. Does not matter which way you write it. So on your calculator, you're going to press that stats button, move over to the test tab, and here this time we're going to select the 2-sample t-test. Make sure you pick the t-test, not the z-test. So your screen should look like that. Make sure you've tabbed over to the stats side. So our mean 1 will fill in as the 0.85 and SX1 the 0.2. And then we said there was 40 cigarettes was the sample size. And then 1.3, 0.18, and again, 40 cigarettes is the sample size. And our alternative hypothesis is that the 2 means are different. So we have mu1 is not equal to mu2. Yeah, so pooled means that the 2 samples have equal variances. This is the only type of t-test that I would ask you to do, or that the IB will ask you to do. It is always yes for pooled. Always yes for pooled. What's the confusion, Alex? This is the final. We're just kind of like walking you through as we're filling things in. All right, let's see the result we get then. Yeah? So take a look here. So this is our calculate, and this is our drawing. What number are we most interested in here? The P, the probability. What's that probability saying? Real close to 0, right? Which means we have evidence in support of the alternative, which says that these two cigarettes really do have different nicotine levels. That means somebody's, like spiking the punch, so to speak, there. Yeah, so we've rejected the alternative, or the null, and found evidence in support of the alternative, which says that the nicotine content is different in the same cigarette brand between two different countries, which means somebody is playing with the batch and probably breaking some rules by creating stronger cigarettes than probably allowable under law. So as a regulator, this sounds very much like something we'd be doing, right? Notice that when we compared this number P, we were comparing it to 5%, 0.05, which it massively comes in under. All right, we're going to stop here for today. This is far enough, I think. Now, I'm not going to assign any homework for 13 yet because we still haven't gone through. We still have a lot of slide to go, right? We're on slide 29. We still have 44, we have to get to slide 44 and then do some in-class examples. So we're going to stop here. This is a good stopping spot as we've done 1 sample and 2 sample t-tests at this point. We're just working on some examples. But if you have not come up with an IA or even proposed an IA yet, like start getting those thinking caps churning. If you want to talk to me about something before you write it, that's okay. That's what we're giving time in class now to do. If you're in the process of going back and forth with me where we have like something that it sounds like it's going to work, but we're going back and forth about how you're collecting your data or what data you're collecting or whatever, I am now available to have in-person discussions, which are